Standard RNN gradient flow. Standard RNN gradient flow. So this red mark is the gradient flow. This is the total standard RNN input vector from x0 to xt, h0 to h1, h2, and ht. This is weight of the node W sh. SH in between SH, here, that's it. Allah. This one H0 to H1 WH. Here also same. So now this gradient flow against this is back propagation. Forward propagation function going on. That's why due to back propagation only we can reduce the loss. That's why we are using gradient descent. Computing the gradient with respect to H0 involves many factors of WHH plus repeated gradient computation. Computing gradient with respect to H0 involves many WHH. This one, and this one, plus repeated gradient computation. Which one is repeated, coming due to iteration or looping? That one. Standard RNN gradient flow. Exploding gradients. Exploding. Computing the gradient with respect to H0 involves many factors of WHH. Many factors. Repeated gradient computations. Okay, we already have seen above slide, last slide. Many values is greater than 1. Exploding gradients, gradient clipping to scale big gradients. Scaling. Many values greater than 1. Exploding gradients, gradient clipping to scale big gradients. So both are making big gradients, big scaling. Scaling, increasing. Gradients. First one, second one, like this. So increasing. Standard RNN gradient flow, vanishing gradients. Vanishing gradients stay gradients in back propagation only here also. Always anywhere. So computing the gradient with respect to H0 involves many factors of WHS, repeated gradient computation. If many values less than 1, vanishing gradients vanish. Activation function, weight installation, network architecture. If many values greater than 1, then gradient will be increasing. Here gradient vanish. Activation function, weight insulation, network architecture. The problem of long-term dependencies. What is the long term dependency? What is the problem for long term dependency? Dependency is there, but long term. How? Why are vanishing gradients a problem? Why are vanishing gradients a problem? You know? Why is the problem? Question mark. Multiply many small numbers together, then errors due to further back time steps have smaller and smaller gradients. Bias parameters to capture short-term dependencies. Why are vanishing gradients problem? What is the problem? Multiple, many small number together. Errors due to further back time steps have smaller and smaller gradients. Smaller gradients. Bias parameters to capture short-term dependencies. This is the method. Small numbers, then forming here, then another one finally. Bias parameters capture short-term dependencies. The problem of long-term dependency, the clouds are in the yes, clouds the best example. What will happen? Rain will come. Same. Why are vanishing gradients problem? Multiply many small numbers together. Errors due to further back time steps have smaller and smaller gradients. Bias parameters to capture short-term dependencies. The problem of long-term dependencies, the clouds are in the small number of together, small number here vanishing. Errors due to further back steps have smaller gradients. Bias parameters to capture short-term dependencies. I grew up in France and they speak fluently like this. Here small, here small, here small. The problem long-term dependency. X naught happens, X1, Y still kept, and then X naught, X1, Y2 cap also happens. Small. Trick. The active functions. Three forming. They are functioning here. First one, the sigmoid derivative, tan H derivative, ReLU derivative. So, sigmoid derivative, how much? This much only, 0.2 approximately, 0.2 to 0.5 like this. Tan H, this is another tan H derivative. This different bell shape, this one ReLU derivative. Using ReLU prevents F dash from shrinking the gradients when X is greater than 0. That's why we are preferring ReLU. If we are preferring ReLU, then prevents the F dash from shrinking gradients when X is less than greater than 0, then shrinking will not happen. Gradients. Yeah, first we have seen, no, here, what will happen? Yeah, less than 1, vanishing gradient. So, using RLU prevents F dash from shrinking the gradient when F is greater than 0. Trick 2, parameter initialization. Sorry, parameter initialization. Initialize weights to identify matrix. Initialize weights to identity matrix. Initialize bias to 0. Initialize weights to identity matrix. Here diagonal all are 1, that's why identical matrix. Initialize biases to 0. This helps prevent the weights from shrinking to 0. This one will help for shrinking the 0. So, trick 3, gated cells. Idea, use gates to selectively add or remove information within each recurrent unit with gated cell, LSTM, GRU, etc. Gates optionally write information through the cell. Sigmoid neural net layer, point-wise multiplication, long short-term memory. Long short-term memory. It means what? In name itself is there. This is the short-term memory, but it's something long, not short. Short-term memory only. For example, not like that. Sometimes like that. This much time. Increasing. For example, 5 times. This is 1 times. Short time. Sorry, this one. Networks rely on gated cell to track information throughout many times steps. LSTM, long short-term memory networks rely on a gated cell track information throughout many times steps. Long short-term memory LSTM. Long short-term memory LSTM. Gated LSTM cells control information flow. Gated LSTM cells control information flow. Forget, store, update, output. First we will forget, then storage, then update, then output. LSTM cells are able to track information throughout many time steps. Cells to track information throughout many time steps. XT, here only no. This is the gated cell. Okay, so here apply gated cell, LSTM, total. LSTM cells are able to track information throughout many time steps. So we have not directly, So in TensorFlow, what is the code for this syntax? TF for TensorFlow, care of the library layers, that is the layer